Good morning. Welcome back from my side. I hope everybody has a good sleep, despite all the theory we had last time. And I hope you are a little bit interested today in seeing a little bit about the applications that we also explored at the end. Because today, all over the day, we will do classification of those data sets we just had. Oops, yeah, sorry. Better now? Ah, yeah, I see. All right. Okay, so the plan of today is really looking at the data sets we explored yesterday. So we will do a little bit of an introduction basically to support vector machines. But before we go into detail, which really takes long in a sense to get you all across, the support vector classifier, support vector machines, kernel methods, and so forth, we will stop early and we'll do some serial runs. There's a tool called libsvm. And basically then we will explore what it means to do some, different aspects of SVMs. And then in between you can do your runs. And at the end we will do then parallel runs for lunch. So that should be a little bit the plan that we will have in this lecture. So that there's always a nice mix between theory on the one hand and then also practice on the other hand. However, before we dive into the material of lecture 4, which is really about now classification challenges and solutions with SVMs, how we overcome them. Let us review a little bit what we had in terms of the theory, just to connect that what we do actually in the theory matters also today. So we have the core building blocks, if you remember, that we want to approximate, in a sense, an unknown target function. But if you really are, look into reality of data sets, we know that it's not really a function, right? There are sometimes data sets where the same x needs to be going in and different y's out, which is mathematically not plausible. So that's why we call it a target distribution, put a probability distribution around it, and are safe. Then we said we expect also some probability distribution on this data set. It's not that we say exactly one specific probability distribution, right? So we say that still there's the probability that those data sets that we have, and the x1 up to xd, and the whole data set is derived from somehow the same function, so the probability of them would be not something which is completely out of scope, completely random, completely somewhere else. So we expect somehow that this is helping our pattern to be detected. Then we basically said we have our tool set where we work with. We said our hypothesis set could be artificial neural networks, could be support vector machines, could be deep learning nowadays. And even if you look inside a model, all of them are H's. If you look inside a model, what we explore today, basically in all the lectures, is even support vector machines. You can have sub-categorizations of support vector machines, right? There are some of them which basically allow some errors, soft margin, hard margin. All of these would be different models we will explore today, and all of them will be also different H's. Hence, we came to the problem of having infinite amounts of models to our disposal. So how in the world should we know which one to pick? And basically, what if you have infinite number of hypotheses in a sense, how we can get around this? And the trick that we did a little bit was when we kind of looking at all the hypothesis set and going through our data set, we actually don't care about many of these hypotheses, right? Because they only care if they touch our data set. If we see suddenly that our data set changes class, if you remember, right? The blue point getting to red, or the other way around. So this is something where it's interesting. So in this sense, this mfollow we could bring back on this interesting growth function, which is also depending on n. However, we see the dependence on n on the data set is still very, very strong in learning. And a couple of people I talked to yesterday were saying what happened if we have two less samples. And this is the equation, which is here. You see the modified Höfding, but here really the Vapnik-Chervonenkis inequality. If you have too little samples here in n, that basically means you cannot learn. Why? Because then your probability of being correct, basically in sample, or deviating basically from the out of sample, that we will never know, right? This is somewhere new, unseen data. It's bigger than some tolerance in the absolute values. That would be some probability which is completely meaningless. It's to the minus n here, right? It's a negative exponential. In this sense, we have to be careful about when there's not enough samples to train, then we better stop and don't do machine learning, right? We need a certain amount of samples to really learn, and this is the explanation why we can do this. And yeah, how we learn was basically very simple. We had kind of two key ingredients, I would say, why we can learn. If you remember, the probability was a little bit related also to the fact that when we do something in sample, typically out of sample is following suit. And because of the absolute values here, for instance, you can also put it the other way around, of say everything out of sample will be mostly like or approximately like we do in sample. So that is very nice. That is the first building block in learning. Now the second building block is practically. So when we have E in, basically the in sample that we can touch and work in our data, we can knock that down. The error in sample, right? When we basically do that with the first building block, the out of sample will follow suit, right? And we kind of evaluate this with our test set. If you remember, we throw that in the corner. We kind of simulate with this unseen data. Now, when you see today in validation, there's another trick how you can estimate the out of sample performance, but we will come to this in lecture 6 with validation. This is now the, let's say, very simple walk through the statistical learning theory that it takes like 4 lectures, right? So it's admittedly very short here, but it carries the essence of some of the practicalities, like for instance the very important dependency here with n, which is very important, the number of samples for learning, and secondly, why learning can be never really 100%. And this is what we call in machine learning the PAC statement. It's probably approximately correct, right? And we have here the probable, and then overall here is this approximately allowing here some error, but never you would go to a machine learning problem and say, oh, I have 100% the solution. Why not? When I have 99%, 100, it sounds like overfitting, right? And this is where we left in the last lecture. And this was a little bit like we had a nice video and really lots of unresolved issues with it. So we have to a little bit explore, again, overfitting or what the problem is it before we really start then basically with the support vector machine and so on. That's why we start a little bit here today in the challenges, looking on the practical problems that we have, and 2 of them basically are here that you already a little bit know, the nonlinear recepable data that we have, also alluding to the applications we had yesterday evening, right, with 52 classes, very complex, so there's definitely no linear decision boundary. And second, the problem of overfitting needs to be very carefully looked at if you want to go to practice in machine learning. It always sets aside the beginner basically from the real practitioner that is doing it. So we look a little bit again, and with this I would like to carry with you some of the first aspects of how you do regularization, right? So this is something, the regularization approach will be here and there, more in lecture 5, right, when we talk about real support vector classifiers, but alluding a little bit to this and also pointing to lecture 6 when we have validation, because regularization and validation are both basically targeting overfitting. At the end, just again the model as overview before we then really go into the maximum margin classifier. And this is a sub-fraction of support vector machines. So everybody knows support vector machines, right? You have heard the name? Okay, who has used it? Who has used the kernel method? RBF kernel, SVMs? Okay, right. So this is kind of the concept behind it, that you have, let's say, 3 stages until you really call something a support vector machine. If you're a little bit more in the literature, you would say that is the first one which has really a hard margin, very similar like the perceptron, so to speak, a line that will be established in a very systematic way, we will learn. Then we have the support vector classifier, which allowing errors, introducing a soft margin coming in lecture 5. And then in lecture 6 we have also support vector machines. But however, a support vector machines is only called a support vector machines if you have kernels inside that are not linear. Right? It's a terminology issue that many people talk about support vector machines, sometimes don't even use them and just use support vector classifier. However, it's maybe a technicality still for you important when you here and there read some books. So we look on the term support vector machines and really make it accurately. And then before we really dive into the geometric interpretation, which is very nice, depending on the dot product and so forth, we will have now applying the classifier to data sets. So that in the morning you can already do serial stuff with libsvm. And while doing this, we will discuss it. You will see the Iris dataset with the libsvm. And while you can experiment with the serial ones, I go more into the geometric interpretation and actually show one of the optimization problems that is behind SVMs. And at the end, we then again go to the fact and using the bigger data sets that we had, like Indian pines yesterday in Rome. And then we'll again explore some limitations, right? Where we say, firstly, this maximum margin classifier is not really interesting in a sense because it's a linear still problem here. And secondly, the problem is that the Indian pines need really computing power. Hence, we start off using the cluster again, right? Not in an interactive session way with libsvm, but rather with psvm. So this is the kind of walkthrough to today. Let's get started. Okay, good. Right, so some of the challenges basically that you have here are listed when you face a real data set problem. These are very general, so you would have a probability that you will actually find several of those when you now access a problem. And just yesterday I talked to someone who was, I think from the bio domain, genomics, genetics, right? High dimensionality of data. Right, so this is an extremely good case and a good example where high dimensionality of the data is. So the models that have to cope with this run into the problem of course of dimensionality, need much more computing power. So these are all challenges basically that you can explore. I don't want to talk with them in detail because in a sense they are sometimes alluding to data management problems, or as I said yesterday, we have good infrastructure in place here, right, with HPC. This is of course very nice, so some of these things help us to really cope with, for instance, the scalability, like gigabytes, terabytes, petabytes of data that we are facing now to analyze. We have out-of-code CPU strategies, things we now use with the GoLED cluster today, which really helps us to cope with the memory problems you would otherwise have using, such data sets in MATLAB or R, because it's just serial on one machine will not work. So high dimensionality we'll discuss. Heterogeneous data comes more when you now pool data, like data fusion from many different sources, and you want to understand a problem. So, and last but not least, you have often this problem here with data ownership you run into. Even if you want to work with some data, it's often that you can really access the data, right? It's often in industrial use cases, medicine use cases. One example is that we talked to one of the pharmaceutical companies and asked, can we see the data for the studies that didn't went so well, right? Because you can also learn from things that failed very much. But of course, these are not existing, right? So you see that this data is not given out sometimes to you. Even if you would think there is a good idea behind it, it's sometimes hard to do that. Of course, in the moment, we see there are more open data. So there's a movement of really quoting authors that actually created data. And if you remember yesterday, we had the labeled data, right? Which was really kind of costly, pixel-wise, going to Rome and say each pixel is a building, a tram, a water. So this costs time and effort of scientists or of people from engineering. And so quoting them for all this work is something which is now much more required if you publish, if you basically have work in the field. But these are more general challenges you will face if you do real data analysis today. Let us come to two more specific ones, which are much more important. We left basically in the beginning of lecture 1 with the kind of case, it was everything nice with the Iris dataset. It was like linearly separable, we can have a line, and of course this was very nice. So in practice what you would have, and we have already discussed it a little bit in one of the questions, already alluding to this, we don't have the case normally, right? And if you just put the Iris in another, let's say, class combination, if you remember, we had the two class combinations you will also work with now today with SVMs, where I put one class firstly out, I sampled that out, because the other two were linearly separable. Now I sampled one of them in again, and you see suddenly they have an overlapping, right? So how should be a linear decision boundary fit here? No chance, right? You will need something which would be very wiggly again here. But what we learned also about this wiggly curve yesterday. Someone remember the very wiggly curve? Yeah?
you have to be careful not to overfit.
Exactly, right? So this would be, again, a very bad thing as well. So, I mean, of course, it would be 100% perhaps here in sample, omitting a little bit this, or almost 100% in sample. But what can we expect, right? We can expect that the net spread point would be probably here or so, and this would be already misclassified. Very bad linear decision boundaries. Same goes with the green ones. There's a highly likelihood that probably here will some green guy follow up. So what can we do? And there are several methods to actually cure this problem. So one of it is, of course, thinking about we still do a line and don't care. So we allow some error to happen, to be, in generally, more right. So this is not completely obvious to you, but we will see how that materializes very beautifully in the SVM approach, where we switch from something you can call a hard margin and a hard decision boundary to something where we say it's a soft decision line, basically, and allow some error to happen. Of course, when you do too much error, that is now the flaw and the drawback of it, then your model would be equally not good, right? So there's a kind of parameter now we have to find out, we have to look at and actually explore what could be right values. But this is a much better approach, still having, in a sense, a linear decision boundary, allowing some errors to happen. And this is what we establish all over the course. Just here, perhaps a little bit a kind of addition that we also yesterday already discussed. If you think and remember about the perceptron that was always doing a line, you can now actually do it something similar like we have just here on the slide, that you do still a line and you let the perceptron work, and you would basically measure at every time step with the pocket algorithm, as it is called, the error. Right? And if you remember, we have this error measure, we can always go with our supervised check. What is the overall error in the moment? So when I do all of this, it will never converge, right? But when I have always the error measure, I can put the best error measure and the parameters of the perceptron in my pocket. That is the idea of this pocket algorithm. And let it basically converge. It will not converge, so no exit strategy. What will you do? We just stop at some iterations, right? So let it be 1,000, let it be 10,000, we just stop. And when it stops after 10,000, the model could be very bad, right? It could be that we end up just that the decision boundary with a vector addition or subtraction will be ending with a decision boundary like that. So that's, of course, very bad. What we do, we go to our pocket and know the minimum error we had with these parameters was the best we can deliver. And this would be something roughly like this in an ideal case, right? It would be still a linear model. Here and there are misclassified points still, but the error overall, because you measure it with it, is basically still the lowest, and you report that. However, this is, of course, again, a very trivial example and a very, let's say, minimal algorithm. There are much more sophisticated algorithms to cope with this problem, and the support vector classifier is one of them that we will explore today, which allows a little bit error to happen, introducing a C parameter where we have a budget for the kind of, let's say, violations of the decision boundary, so that we don't do too much and basically not too less. So it's a parameter C we can play with, and we will today in practice. So this is a pocket algorithm just for you to take away. Nothing else. This is still the perceptron model. All what we changed was the perceptron learning algorithm. We put a memory cell, if you want, a little bit, which is our pocket, a bit computer science smart approaches inside, and then you will report that what is in the memory. However, let us look a little bit more now on the second problem, because this is a bit more tough, and in a way, as I said yesterday, it's the biggest problem in machine learning, right? So you have to understand this very well before you do reportings to your customers, or when you go into the job and report something to your boss, that you have a very high accuracy, because chances are you again overfit. And the reason for overfit is basically noise. There are different types of noise I would like to talk about. So here's an example, again, a little bit more, let's say, as an illustration. When we have the target that initially was creating the data points, which is this parabola, this target here, we see overfit usually happens when we have a very wiggly curve that is, let's say, polynomial to some extreme degree, or something like this, while in reality it was just a simple parabola. So this is a kind of typical, let's say, illustration now. And in the sense, you can see overfitting tries to fit the noise, everything which is disturbing kind of those that are not directly on the target, And over, learning extremely long, for instance, would bring more and more the fact that you align the model to all these noises, and this brings this really poor, right? Also, if you have just too little samples, that was discussed today also, and yesterday, then you also overfit because you just don't have any other samples, so you just align your model basically with this couple of 3, 4, 5 points. Hence, here's the Vatnik-Chervonenkis inequality saying, stop learning, don't do machine learning. You have not enough samples to do. Right? There are tricks like data augmentation, also that we have discussed yesterday in one of the breaks with some people, where you can have more data basically created out of a couple of samples, but if you have very few samples, like in this example here, you would have just, let's say, 5 dots here, then it doesn't make sense at all. So these are kind of the parts where you do overfitting in a sense. And this is basically showing, basically with the fact that in a sense you really train on the in-sample, right? And you think you did everything right. And this is why we have sometimes this 100% and 90% and in-sample, and would say, yeah, we really did everything right. But the problem is if you go out of sample, you would see the next points really don't fit the model. Good, so much for this, and how it affects basically our training time and error is a very nice graph here, where you see it's really a problem stopping at the right point, right? Because if you also remember, of course, we need iterations for an algorithm to converge. Like the perceptron, when we just use a perceptron once, nothing will happen very much, right? So we need the iterations of the perceptron, we need the iteration of the support vector machines to optimize, to learn from the data. So we need the training time, right? So this means we cannot stop before, let's say, a certain degree, because this would be just bad generalization. We didn't learn anything, right? We cannot create a model out of this. On the other hand, if you learn too much, if you continue learning and learning, it's very nice in sample, but we see that suddenly we memorize rather and overfit, and out of sample would be then again bad. So this is a trouble factor, and that's why it's also not so easy to just stop overfitting, right? There's not directly a recipe where you can say that's what I can give you. It's something you have to explore with parameters, and we will looking at the support vectors later, right? But this is always a danger part then for you when you see this, and the reason is really fitting the noise, right? And the kind of two approaches we will really tackle today is regularization first, then validation. And regularization is a very, let's say, theoretical part, often encapsulated in algorithms, in neural networks with weight decay, weight stop, or in the support vector machines is also a parameter, the C, allowing some of the errors to happen. On the other hand, validation then a systematic approach to find these parameters in a systematic way, and with this helping that a good model will be found. More of this all over in the lectures. So let us look a little bit about kind of the intuitive solutions to actually prevent overfitting and what you can basically do to understand this problem better. And here you would say there's a technique called early stopping at some point in time. And this is something which is usually very good, so you just stop after some iterations. It will be better to stop after some iterations than continuing for lots of time, because mostly what will happen is that it relates also to the model complexity. You go up and go up, you create better and better models, they kind of tend to be more and more complex, and with this you have again the fact that you basically overfit, because in a sense the data is not reflecting the model, right? An example would be then again polynomial to the degree of 4, to the degree of 4, 5, 6, 7, so you add kind of the model complexity that is meant by this, right? Here are the linear models, then suddenly I go more sophisticated polynomial and add and add and add. So, and support vector machines will be then more complexity and so forth. So early stopping is, for instance, a regularization technique where you have some, let's say, handle here and there on the test set, so you can always check, is my accuracy going, let's say, in the test set completely out of scope, or where am I in terms of, having perhaps roughly this point hit here. And this would be, of course, the optimal that is hard to be found, right? That is not something which you just can know, okay, my regularization pattern is 0.5 everywhere, or in this particular model. You have to search for this point a little bit. And we will do that all over today, actually, to do this. Then the kind of reason for overfitting was the noise term, if you remember. So what is about these noisy targets? We have here again the example that you see here with the noise. So we have kind of the typical target, kind of very simple model, and we overfit by fitting the noise. But what is kind of, noises are there? And this is an interesting takeaway message, that there are kind of two noise terms, in a sense, that are in the data. Someone have heard from the noise term, noise already in the data? Noisy data sets, okay. There was also someone on data quality yesterday, so this is something where it also basically relates to. So let's basically shift a little bit the view now again to the samples, right? When we do this, we can see there's kind of two different types of noises around. And this is a kind of first example where, you have some stochastic noise where it is basically inside. So inside the data set is something that is very random. And if you remember what I told in lecture 1, randomness, in a sense, is a very bad pattern to be found. And actually here, it's kind of really disturbing the classifier from learning, right? You put some values which absolutely make no sense. And reasons for them could be basically manifold. So one of them would be, for instance, when you have a measurement device, right? Just that we discussed yesterday in the Pangaea case, with the water mixing in the fjords. There's this biofouling. So more and more over the months, there will be more and more biofouling with the buoy that is measuring, right? This will be noise, right? The measurement would be not accurate anymore, more and more inaccurate. And this would be some stupid, let's say, stochastic noise inside the data set that the classifier tries to see as real data, right? So this is the one problem where also it's basically related to overfitting. And of course, if you have really, let's say, extreme values like outliers, we had in one example yesterday, we should always get rid of outliers first before we're putting it in the model. Some are robust enough to outliers, some methods. Still, if you have the chance of indicating them manually, it makes really sense. Because if some measurement devices go really very much in the outlier space, it much more makes sense to perform this before you really do basically the learning process. And it really, as you can see, if you have all these measurements that are very beautifully on the target, so probably created from the function, and there's suddenly these outliers or noises around, of course, the function don't know that we create. So we will fit the noise. And this is also one reason, basically, of overfitting. So the other side of the equation is deterministic noise, and this is a much more harder to understand usually for my students, because this has something to do with our capability, what we do with the data there. And you can compare it a little bit with the capability of a toddler, right? If you now come home after this, let's say, interesting 2 days, and you have a kid and you will explain now, hey, I did machine learning, and the kid is like 1 or 2 years old. You did machine learning and the statistical learning theory is Höfting inequality, and then you ended up at Watnik-Chervonenkis. There will be just a big question mark. Right, Watnik-Chervonenkis, aha, okay, good, no chance, right? And this is what I mean with capability. There is the part of the noise is that basically your function is just not capable to actually get such a function approximated where the data was created for. So it's in the way the other way around, where you would say that the target function f that we want to find is a very sophisticated function, but I use a model like a perceptron or some other algorithm for me as machine learner that absolutely doesn't fit. I'm not aware of support vector machines yet. All I have is a perceptron learning algorithm. So I face, let's say, a very sophisticated function here that I have to approximate. But how should I do this with a linear model? No chance, again. So this is the other way around, where you say that's where also these problems with noise come in and overfitting occur. So it's a different type of noise, but both noises we have in the data set, and that's why basically it helps to don't see always the data set exactly as it is. And this is an interesting concept called regularization. You a little bit go away from the data set and take it a little bit more relaxed. That's the kind of view of regularization. You don't take every sample by heart, because if you take every sample by heart, chances are that you actually fit the noise. This is a noise point. If you have now a regularizing approach and say, well, every of the sample has an impact so much, you kind of as I said yesterday, penalize a little bit all these different ones, with the weights, for instance, in neural networks, or as we see later, with support vector machines, allowing here and there violations of the decision boundary. This is, of course, then helping to get rid, in a sense, of the noise, or don't really take the noise into the model. So these are one approaches, regularizations, we will talk about it later. And of course, validation is then the second cure. So this is really, breaks in learning, early stopping, but you can really see it as penalizing a little bit the model and don't take all the samples by heart. That is regularization. And validation is then much more practical thing, where we then fit basically our data with the best model according to the parameter. This is not obvious to you, that's clear, it needs a whole lecture to get through, but this is what we will do in lecture 6. Right? So you always see overfitting will be combated, so to speak, with these two mechanisms. Right, and now it's time for some exercises. So start, please log in again, just to check if there's, some problem.
For the people using reservations, remember there's a different reservation today. It's 370, not 6.
Yeah, 136, and yesterday 137.
No, 317.
317, okay, today. Right, so we don't run a model yet. What I wanted to check here now is that you can log in, and if you have now problems, please speak, because we then will continue very quickly now in a couple of minutes for the libSVN. If you can't log in, please scream now. Okay, if that's not the case, very good. Before I go here into this particular video, just take away the message. What I will tell here a little bit with regularization, with overfitting, with validation, we will do this concretely on SVMs. But this is a general principle in machine learning, both of them are. So you find that in neural networks, you find that in different models. So that's why I put here a video just for you as understanding what we do here in between is also really basically existing in other models. So if you don't have so much troubles with an account, that's very good. So let's go quickly into this video. It's just a short video.
This is a simulation of a single biological neuron. Information flows in, is processed by the neuron, and the results flow out. This gives the neuron its abilities to react based on previously learned patterns. Technology duplicates this by creating a structure that processes information like a biological neuron does, except this process is mathematical instead. Just like the biological neuron, information flows in, is processed by the artificial neuron, and the results flow out. This single process becomes a mathematical formula that can be used for simple problems. For those that are mathematically inclined, this will look similar to a polynomial.
Short problem with the micro, but you get sound in a minute.
As shown in this graph of an order 5 polynomial. If this is all artificial intelligence could do, it wouldn't be much use. As with the brain, artificial neural networks' power is in connecting sets of neurons together in layers. When you connect them in layers, the mathematical formula becomes something like a multi-dimensional polynomial. This allows complex problems, like what is shown in this graph.
Right, and here I want to stop and make a point. I hope you can still hear me without the microphone. Or it's coming back. The batteries, or? Gives me the chance for getting coffee.
If I get too close to you, it doesn't work.
Then I find bionic parts. Influenza signal. Yeah, we wait a bit because there's also recording, and I think the voice is better than for the recording and also for the people on the streaming.
For the streaming, the mic doesn't matter.
No? Okay. Excellent. But for the recording, kind of.
No, that's fine. It's just for here, but it doesn't work.
Yeah, yesterday were already some things, I think, when I turn.
Yeah. So just continue, it will be fine.
Okay. I will be just louder.
Recording and streaming, it doesn't.
Okay, excellent. So when you think on the back rows, I'm not loud enough, please make this sign. Okay, then I get my feedback that it's not loud enough. I see now you do this, that means probably you can still hear me in the back line, yeah? Okay, good. Excellent. So let's continue. Again, the point I wanted to make before we go to the practicals, what you do here now with SVM, right, is very specific to this kind of classifier. However, you have neural networks, and you have the same problem with overfitting. Especially more with neural networks usually, because you can consider all of this as different parameters. So the parameter here you see is the number of neurons in the hidden layer. That is not obvious to you. That is something what you have to explore with your data set. One parameter that you have to choose in your model. Then you basically have lots of weights to work on. And one technique of regularization, for instance, the same idea in a sense like we will do with support vector machines, or that we have seen in the polynomials, penalize the model. Right? So what's happening is we just get a weight drop here. We just take one out, or take another one out. Or we do weight decay, is another mechanism of regularization, where we have, when these weights are computed, of saying how much strong is a signal, right? We do an optimization there. You cannot know that all in detail because it's what I will talk about next week in the deep learning tutorial. Right? I just want to make you the connection that the regularization approach is here as well. And weight decay would be rather example that also penalizes these weights just a little bit always. Right? Because a signal has been taken up by the data, but all of these data include noise. Stochastic noise, deterministic noise. So it's not very valuable to take all the signals by heart. Right? And by doing a little bit of, let's say, one step away from the data, penalizing, friendly saying in a sense, the model, you prevent overfitting. And this is an interesting aspect, hence still there are lots of parameters for regularization. Right? It's not that you just use one, it has relationships also to other aspects in your model, what you pick, like the number of hidden neurons, for instance, and so forth. So this is a principal idea here of neural networks. And what the guy is saying is not so important, you can't hear it probably on the back anyway. But just take this information, basically how you do it, you combine your data with the weights, you do a summation here, and then propagate data weights and have your output, which is a forward pass. How the error is then basically done is a backward pass, and all of this I will explain basically then next week in the other tutorial. Just more for you, take away message that, again, validation, these are all things that actually take place also in other models. Right, so let's come a little bit shortly to a minimal introduction to maximum margin classifier before we go to the libSVM practice now on the cluster. Again, we are in the space of classification in this sense, so please take that away as a message. And what we were saying, we refine a little bit the term support vector machines, which is usually very liberal, right? So people use support vector machines as a common term for all of these, which is, let's say, really not true in practice. And what we want to explore now is playing with all of these three over the course of today. So we start with the maximum margin classifier, which is basically nothing very much better than the perceptron, because you need linearly separable data. And the only benefit it has, best linear class boundary. So we'll explore that now. After that, in the afternoon, after lunch, we will go more into support vector classifier, allowing errors to happen, soft margins, before we then go very sophisticated in lecture 5 at the end, and then do some validation based on support vector machines, which have actually non-linear kernels. And this is then a real machine, as it is already told. So basically, this is an example where we have already this said in the beginning, what would be the best line, right? And maybe one of you remember from yesterday, what would be now the best line that we pick, right? We have all of these different lines. Anyone want to get you a bit more active? Yeah, please, go ahead.
Well, that's completely vertical.
Very good. And why?
Because it has the biggest distance compared to points on each side.
Exactly. Distance is exactly the right term we need today, right? Margin relates now to our distance to these points. That's why I'm repeating what we basically said yesterday, right? So the kind of, our gut feeling says already this distance here, in order maximizing that in a sense, right? This would be a very good idea to do. And in a way, you would say furthest away from the closest points, if you like, from this decision boundary. There are different viewpoints, but the distance is a key point here. So let's work on this a little bit. There's a concept of sequential minimal optimization, how you optimize this margin. And I will now, while you have already your practicals done and actually started with this, then actually come to this step by step. Right, so this is something which you then know in the end, Lagrangians and SMO. But in order to have some practical view now, we start with the libSVM tool. Right, the libSVM tool is a serial tool and is already installed for you now on GoLab. Right, so when you use it, you need the interactive access. However, I want to just take basically you and show you a little bit that if you want to use it at home, you can use it on your laptop. It's a serial version, right? It's not really a very powerful parallel version that we use in the beginning. So libSVM is open source, you can use it. You can basically, there's for Windows, kind of a libSVM installation. For Unix, it's basically untar and so on. So you would very quickly get to the point of installing that on your system. You don't need to do that now, because we have already done that for you on the cluster. Right? So don't worry, just for you, when you finish this tutorial, you can still work with some of the things also on your laptop if you want. Of course, not the parallel ones. So actually the Unix installation is the same way. There's a nice make utility and so on. This is just for putting you this in the slides. So when you want to play at home after the tutorial to get the knowledge basically into practice, what I recommend, then basically it's important to actually think about this. Important for us now in the practicals, we have always two executables, right? Yesterday you had kind of a clustering algorithm with one executable. Today we have always two executables, two different ones. And they relate to our aspects we learned yesterday. There's always a training phase with a testing phase that then reports us some nice accuracy, right? Think about always you need now two job scripts, two different processes. And we will go through and discuss it, what exactly that is, together now. But this is very important. And there's a small helper function, SVM scale. If you do it at home, for instance, you can do this and try. We discussed yesterday, sometimes it makes sense that the data is between 0 and 1 or -1 and 1, just to make the mathematical more convenient in the sense that we don't have so much large numbers. There's also a tool, or you can download the scaled version, for instance, of Iris also directly from the website. It's all here in the slides, so if you want to do it at home, you can use it. Now what we do now is basically going and looking at these two data sets, right? And if you remember, this one was a very nice one from yesterday, and the slides are, I think, uploaded already, so you can have it always as a reference, because when you now play around with the SVM, of course, we have to think always for this one, it would be probably work very well, because it's linearly separable, the maximum margin, the first small model we will develop together. And here for the second one is basically probably some problem here, because we have still a hard margin in the first SVM, or basically in the maximum margin that we will learn today. It is already prepared for you, so when you go to the directory I show you in the moment, you see that we have already like 20 data points for training and 30 for testing, so it's not very brilliant, but on the other hand it's a very simple data set, right? So in this sense, always think about that you use now these two data sets, which are already uploaded on GoLab and available there, now to actually test your models, right? And the first thing we're going to do is we're using this linearly separable data, which I used today yesterday to show you basically the linear decision boundary with perceptrons. but we use it with the maximum margin classifier, with libSVM. So this would be the first problem we face. So let's get started. The data of the Iris dataset, if you remember, is here in the UGent tutorials, machine learning classification Iris. And here you have your class 1 and 3, right? If you go back, class 1 and 3, this is a linearly separable one. And then you have here class 2 and 3. That's where I sampled back, the 2 and removed 1 in order to make it not linearly separable. And it's always nice once 2 you can always use for benchmarks, no matter what models you do, in order to get, to the kind of this idea of learning what the difference is between both. So we know where the data is, right? It's like yesterday we had clustering here and HPC-UGent and Bremen and so on. Today we will focus purely on classification, right? Hence we use here the classification Iris as a first start with a very simple model. So how we use it is basically something where I recommend for you to create maybe a small script, like here. You see the 1 and 3 class. What I did here is just use SVM train. That's an executable. I show you in a minute how you can use it on Golet. And here's the different types, basically. These, of course, relate to some of the lecture we had yesterday. So it makes sense to open also the other PDF. I will do it in a moment, because the parameters basically are the same with PSVM, is the same with the libSVM, so we can use them. And it indicates basically what type of support vector machines you use. We will do that together now when I do hands-on. So don't worry about this, just for your reference in the slides. When you're at home, of course, you can play around now with these things, right? And here is a data set that you have to give. So this would be one idea how to do it. You don't need to do it in a script, right? This is one just more convenient aspect, that you don't have to type all the time. And you can still type it all the time because in a sense, as you see, there are not so many parameters. So once you do that, you will see there will be some interesting aspects out. And what comes out of this will be a model file, right? And we will look together in the model file what's inside. And the beauty of it is they have the support vectors. And this is a key property of support vector machines, which I will tell you towards the end of the lecture why this is so interesting for us. So how you then go to the next step, and once you have the model, and we will do all now stepwise on the cluster, right? It's just for you to give an overview of the whole process before we go, because we're very much more lively today because we have different processes. We have training and testing, right? And training needs a model file to create it. This is very important. If you don't train and come out with a model file, there was something wrong, then please raise your hand, right? This is important. And then there's kind of the second executable, predict. Also there, I recommend to do a small script maybe. And basically then you can do, the classification, and you get some accuracy out. And what we want to aim for is, of course, when you do SVM predict on this thing, it should be hopefully 100% because it's like linearly separable. Right? So this is an example where it's probably even true because it's linearly separable even if we have 100%. But it's a toy data set, right? Not really a practical one that you see in practice. There will be this input as a model that we trained for the prediction, very important. Secondly, there will be results where basically just the testing process tests each of the sample in which class it would put it. It needs this, if you remember, for our confusion matrix to actually calculate the accuracy. And that's how the 100% is. So these are now kind of a process flow, right? It doesn't make sense to predict before you train, right? You always have training, get the model, predict, and so on. So in a way, this predict is a little bit, let's say, wrongly named in a sense. You could see it as test, but this is how they came up with the name. I don't know exactly why. Here are the parameters. And this is another slide you should basically now in the training. Sometimes I recommend people to do a snapshot on your laptop on that because we'll come all over the day back to this one, right? So it makes sense to do now a snapshot and put that on your desktop because these parameters we will play with, right? You will see here when you do SVM train, for instance, the parameters that you have is here, for instance, which type of actually support vector machine we're using. And here we are pretty settled in using the CSVC. And then here that minus t is now what we will play in over the day, right? This actually shows you kernel. But if we learn basically with a linear kernel, which is not really then a kernel, it's just a normal model, it's not yet a support vector machine, that is close to our maximum margin classifier. So when you start now your first training, please use the minus S0 for this particular type of support vector classifiers and minus T0 first. Right? We will come in the lecture what a polynomial kernel is, what a radial basis function kernel is, so that will be established, at least a little bit mass to go there and understanding. But this would be now the very simple first case to work with. There will be a regularization parameter that we also now discuss over the course, also after lunch, more in detail, which is C. And C is kind of a budget, if you want, for how much error is allowed. Also there I would be talking about more. So in this sense now, take please, if you have downloaded the slides, if not, you just go to the website, they are available there, and make a snapshot of this particular slide 34. Put it on your desktop, it really helps in the tutorial always. Also the people that will come to you if there are problems, you know, usually you always go into the slides and look, did you have done the right parameter? Good, so much for this. The predict is very simple. It has not so much parameters, right? This is now the test set that we have put in the corner. So hence we need the test set, the test file, but of course a model file that you created out of the kind of training step before. And this is a little bit loaded if you think about now it's a job, and it yesterday was somewhere available in a job directory, but this is in the parallel world. And that's not what we're going to use today, because now what you should do now is basically this part here. If you remember, some of you I think have tried it yesterday already. Kenneth has sent an email about that. So use please not the login node, right? Before we now start, not use directly libsvm. First of all, you can't, because firstly you have to load this one where our libsvm is, but use the interactive session possibility that we have of Golet. Right? With other words, you do the following. You start logging in, and please do that now while I'm speaking. Right? That's important now that everybody doing that we not overload the login node with all of us. The first thing to do is log in. When you logged in, module swap cluster Golet that we learned yesterday in order to switch to this particular cluster out of 5. Once you have done this, create an interactive session, and this is what just Kenneth says, we have a new reservation, right? If you have this already in your history in Unix, please make sure that you change 316 to 317, which is a reservation today. And again, like yesterday, if you see there's an error, there is a problem, raise your hands. We have good experts in the room that help you, and this is a kind of environment set up now for us. Here I put also Q sub minus E without this, just to give you the idea if you're at home, you can still use interactive sessions. But today, as we have the tutorial and the reservation, please use this reservation part. What you get out of it is you wait probably a little bit because you get scheduled, but with a reservation, it's very quickly that you get access. Right, and so everybody has done that. Is now an interactive session active? Okay, is there someone who has a problem of creating an interactive session, like I pointed out here with Q sub minus E? So everybody has an interactive way, very good.
Put it a little bit
bigger, okay. Yes, so know how that works.
Really should do it yourself.
Yeah, I think one idea could be also that I do it just myself, and then I can increase the font size. Otherwise I can have the snapshot bigger, but I think it maybe makes sense that you do that here together as well. I work on it, so 1 minute. Then you can look on the zoomed in version.
This is also mentioned in the email I sent yesterday.
Yes, exactly, though there was some...
Swap to Golet and do a Q sub dash capital I with the reservation.
Is it better visible, this font size, or even bigger? That okay? On the back? Okay. because it gets a little bit also for me hard to look at this laptop when I have such big fonts. But the typical thing we know from yesterday, logging in, and then module swap cluster bullet. Just to switch. Now we are there. Here and there you could do make a clean if you want. And now the new commands that you have here from the slides. So instead of creating a job script and everything, what we have done yesterday, we get now from a scheduler an interactive node for us to play around, basically an interactive session. Hence we need basically this interesting command qsub, not with a job script, but with E, and this is very important, it's not an L, it's a capital E, right? Because here in the slides, here and there from the font wise, it looks very similar like an L. Minus W. X equals Lex. And here's important now that you switch from 316 today, completely the whole day, always 317. Right? It's a new reservation.
Take half a minute or a minute before your job gets started.
Yeah, so what's happening now is the scheduler gets all the requests for the interactive session, like in my case as well. So we have to wait. There's not something you can do right now. But hopefully, because we have the reservation, we will be scheduled quickly.
Morris, before the 3 it's a dot.
Oops.
So yours will just wait for it.
I did it. No, I did a column. But it's very funny that it's still not there's an error.
Once your session starts, if you run host name, you should see node 2 and then number.
Yeah, sorry for that. Very good observed, actually. Thank you. Good.
So somebody was copying your mistake.
Yeah. Sorry for that. Right, so now we have our session. That's very nice. Again, make it clear here. Still, if you do now SVM train, oops. Yeah, with the resolution, it's a bit problematic for me here, but let's see how we cope with it. SVM train, it's not there, right? So we can't do it. What we first have to do is load our module that we have already prepared for you, which is a specific libsvm that you also can download yourself, as I just explained. But here, for convenience, we can already use what's on the cluster. Also here is very important that you see, don't make any mistake like myself with a dot in terms of a column and so. Every little capital or not capital will be important. So now we have this, and we have SVM train that we can use, for instance, looking at this. Yeah, okay. So here you see just what I have on the slides, right? This is very important for us, the -s option. Here we need a 0, -t option. In the moment we stick to linear kernels, very not sophisticated, right? But that is what we're going to use basically in the first part, what we learned with the maximum margin classifier and so forth. So once you've done that, it's time for us to get started. We have now everything we need. And of course, feel free to, for those of you that would like to, already start to some of the things, just go ahead if you know and are familiar with working with the SVM train, for some of you. With the others, I will now do a step-by-step walkthrough, where we said from the data sets, we want to firstly have this one, right? Which is the one where we said it's linearly separable. We assume that the maximum margin classifier here should have, well, actually 100%, right? So this is interesting, and still if we use a linear kernel. So how we do this would be then basically we use this data set with class 1 and class 3. for that. Right? So what you can do now, for instance, is copy from the apps directory in our, again, tutorials, machine learning, there's a classification, iris. Oops, no. With tab you can always see what is inside of this, and what we here want to have is in the first place now iris 1 and 3 testing and training, and copy that basically to your home directory. So iris class, or you basically can also do the following if you want, because we have an interactive session to speed up a bit and copy everything that you have inside the that you have basically in this directory, and then to the point location, which is your current directory, right? So you're now in this interactive space on this node. So we need to copy the data basically on this to make it a bit more cleaner and more easier. Look. No, just like this. Sorry, the resolution is so big that it's a little bit hard for me on the laptop sometimes to see what I'm doing. So what you have now, when you copied that, you have all the data files basically in your directory and can, easier work with it than always specifying /apps/ etc. So this is a little bit better for our part here. And what we do now basically is just nothing else than we know already, PSVM train. And we said we want to have -s and -t as specific ones. What are the specific ones? Again, that is now the point where I said you should take a snapshot of this interesting slide here, which is this one. I do it myself now so that I always have it. Because here you see the parameters, right, that we will always use again and again, and will modify a lot. So having this done, what I recommend to every one of you, we can see -s should be 0, right, indicating that we do CSVC, a specific type, so to speak, of this classifier. And we will discuss over the course of today now more and more of the substance. It's just that you get early also some practice here. So for our executing, that means -s 0. And then when we look on the parameter t, it's about kernels, but we have no kernels yet. I will explain the kernels in lecture 5. Hence we use a linear kind of decision boundary, which is just basically this, what you see here, u and v, and we will come in the theory very soon in describing what exactly that means. So also here you pick 0 as initial start.
Morris, I think you need to drop the PI in front.
Oops, yeah, oh, I'm so sorry, I'm so much in the parallel world, yeah. Thank you very much, good feedback. Of course, we're not parallel yet, right? So I mostly use parallel computing, so that's why my SVM train is, let's say, the serial one. I tend to forget that. So we have now the serial executable, we indicate this kernel, we indicate this particular model. So what's missing? The what? The training file. Exactly. Now we need the training data, right? And we said we want to have this one, this particular one, iris class 1 and 3, because it's linearly separable. And use the training file actually for doing this. If you look inside, you will see nothing else than the libsvm format from the flowers in this specific case. So having done this, we basically have here all fulfilled our kind of basically usage of that. So let's go. And it's very quick, right? It's basically already done. Here's a very difference between, of course, Indian pines, Rome, and so on that we will use in the other lecture. Indian pines is not really computational complexity. However, it shows you already a few things. First of all, what we see is the total number of support vectors. 4 of them should be in our model. right? And this is a little bit something I will now explain. What is exactly a support vector in theory and so on, but you know, can play around already and train your data. And if you look, these are kind of specific aspects from the optimization that takes place. So ignore that for a while. We will come to this later when I show you how SVMs actually work. But basically, I have here already an indicator total number of support vectors 4. So when we now enter in our model file, what would we find? Someone has an idea?
Yeah.
The 4 support vectors should be there. It's real data. So let's look in the model file that was created. You see here, basically somewhere, it should be a model file. And I have to scroll here, I think, a little bit. There? Yeah. So let's do, for instance, a more. On this one, you see that was just created, the model file. Everybody from you should get one. If you don't get a model file, raise your hand. Right? There's something wrong with the SVM train. Doesn't work in your case?
You're stuck after the copying part.
Okay.
You know that, but you went too fast and so you...
Oh, sorry. Yeah, in this case, also raise your hand and give me feedback if it's too fast. For some, of course. But also use the slides, of course, right? The slides have the PDFs where the steps are all written in, how you submit and how you do this, right? Because then you have been stuck, for instance, at this part, right? So a few. So submitting is now the problem. You have the interactive session.
No, the last thing we did was the copying of the from apps, that's Iris, and that's the last thing.
Okay, and this is now the next thing. So basically, it's just we train now, or we basically start the process of training. Oops, that's a little bit. Let me following. So basically you see now the copied stuff should be all in your directory. That's why we don't need to have any more /apps/ etc. When we references, you train and use the executable SVM train with a specific type of the SVM and basically with a kernel 0 which indicates linear model. Right? If you just use this and then this training data and hit execute, it basically should work. And can the people raise hand that didn't do that, so that had problems here of submitting? Okay, there's a problem. If you could help, thank you. Just checking why that is not working. So normally that should work. And when you've done this, basically everybody of you should get an interesting model file. Right, so let's wait. As we get the feedback, we're a bit too quick for some. 1 minute and then we continue. For those of you who are already kind of interesting, look a little bit in the model file that is created, like, you know, more and then model file or something like this. Is there anyone that has not the model file created, apart from those that are just in help? Okay, everybody has a model file. Excellent. Okay, good. Okay, the PSVM train works on that. Yeah, okay, on this. And we have no problem anymore. So that means largely everybody has done the training and everybody has the model file, right? So let's look into the model file. And this is not a surprise to us, really, right? Which is now in the model file. You have 4 support vectors. Now the interesting property I will alluding to in the theory is these are in-sample data, right? The support vectors are taken from basically the data set, and we will establish that now with mathematics and so on. We have the number of support vectors, which are the total number of support vectors 4. We know the type of the kind of model that we have is an SVC. We know the linear kernel. We know the number of classes, so it's a 2-class problem, right? So we indicate this in the moment. We will later go to 52 classes and so on. Not really trivial. This is a very trivial example. Still, these are things from the optimizations you don't need to know, so ignore that for a while. We're not there yet. And of course here that gives you the class labels as well. So class 1 label and class 3 labels. So that is already your first support vector machine you trained. Congratulations. It really takes a long time, like almost 1 second, right? So you see it's serial. This one is not really a challenge where you need parallel computing. Right, so with the model file created, we can now test if that is really a good model for us, right? So is the support vector machine really good in this sense? And that is what we can do with SVM predict. If you remember, what we need for that is the model file. So let's use it. And what you basically can also use here is something we call results, the output file. So what is the output file? It will write inside for each of the sample what the support vector machine in the moment, the trained well, will think it is. So what you see there inside is just the labels in which class it was put. So in a sense, it's not really useful as a human readable thing, but if you want to have more sophisticated aspects and showing the results for each of the sample, you can use this information which is in the results, which is an output file you can name as you like. I usually use results, for instance, from text, but there is not a strict requirement doing this. Oh no, sorry, of course, what I did forget here, sorry, in the resolution, the testing set, right? See, first we need the model, but we need also the testing set, right? Otherwise we cannot test against the unseen data. Hence we use now the testing data, which is in the corner, put them back, and we have it basically here, in the other data set that we copied to here. Oops. So in the end, we predict, we use a testing set that is in our directory, we use a model that we just got out from the training, and in the results will be written what type of class it is and so on per each sample. Now here we have also directly the results, accuracy 100%. Can someone explain why that is now the case? Okay, they're just two at the same time. I think the last time I had you, now the lady.
Because they are linearly separable.
Linearly separable. Yeah, it's a bad word. I know. Absolutely correct, right? We kind of were assuming that. It's a very nice data set, and let's look a bit of just visually, right? It is here also on one of the slides, if you remember. Whoops. Here in this particular one. Yep. We have done now our first model in the first case. And now we would say alarm bells, overfitting 100%. I come to you in a moment, just to make a short point, that this is of course a toy data set, linearly separable, linear kernel. So what we have done was basically now find the best line. Very similar like the perceptron learning algorithm, but the perceptron learning algorithm would stop somewhere. Right? What the machine learning in the maximum margin classifier is now doing is this thing we discussed here in theory with this particular notion. So this could be perceptron learning algorithm. This could be the perceptron learning algorithm outcome. We don't know. It will just take one misclassified point and classify as long as there's no misclassified points yet. So we can end up like this, or we can end up like the other one. Now what we done just now was basically this. We take the maximum margin, and it will be established now in the theory part, while you can play around in the background more with the data set that we have. and we'll create exactly this by having these margins created and picking those as support vectors. So this is not the data set that you have here now. We see there are 4 support vectors, so there would be probably something like here, another point that is sitting directly on the margin. But that's what we will do in the theory. Now you question them.
The 100% accuracy on the test set, that's not always the case, right? Even if they are linearly separable?
Well, it depends, of course, on your model. That can be possible, yes. Or what do you mean? It is possible when your data is linearly separable and you have a linear model, then it should work.
Yeah, but it's not always 100% accuracy, right?
Well,
on the test data.
Well, usually, if the testing data should be also linearly separable, of course, that should be the case. There could be cases where you maybe don't train enough, right? Where you don't have iterations enough, where you just do early stopping, and maybe that would be the bad generalization fact that the line would be not really trained enough, like the perceptron will be stopping somewhere. Even if it's linear separably, it didn't converge. And with this not converging, it would be, of course, not then 100%. But we will do now an example which is non-linearly separable, and there you will see that the 100% is not possible because it's not linearly separable.
I'm just thinking, imagine that one of the red points in your test data set is actually on the right of your separating line. Then you don't obtain 100% accuracy, even they are still linearly separable.
Yes and no. So basically, again, with the perceptual learning algorithm before convergence, that could happen. With the machine learning, in the maximum margin case, that cannot happen. In the maximum margin, and this is why we don't have any theory yet. I will explain now how support vector machines work. They will take the most closest point, even if it's in the test set, and you basically have then the margin. But with assuming that the test set is also linearly separable, it will be highly unlikely that this is basically the case. So I could consider, let's say, in very artificial case, that these are directly at each other, where you could think like the test set would be then really in that space, but then it would be not anymore really linearly separable. Right? So it would be, the point is basically using your test set, and there's some point in that was not used for training. Right? And this would be a very, very rare case that this would be happening. Because then it would be not anymore this kind of maximum margin aspect in it. But perhaps when we go through the theory, it becomes more clearer. Because what the support vector machine is now doing, it creates a buffer. Right? And the buffer would be meaning the test set is very likely to be on the right set of the margin. Now there could be a point very, very, very close to the red one here, basically, even if they are linearly separable, and the buffer would be then kind of partly back. And this is something where we will talk about, right? So this could happen, but really rarely. Because then it's a question what you really consider linearly separable. And basically it's the same, or it's very close to it. Yeah, another question.
I think the point was that it can happen if it happens to be that your data are, let's say, very much different. Let's say the green one are very far away there and the red one are here. Then your optimum margin will be more or less in the middle. But then it just happens to be that in this case you have, I don't know, somewhere
an outlier, for instance,
to the right.
Yeah, that would be the outlier.
The margin. They are still linearly separable, but it can happen that they are misclassified.
Right, yeah, but it would be very rare, firstly, because we have the margin, we will talk about in the theory, and secondly, the probability that the point is really so far out would be just really an outlier then. So in a sense, yes, it could happen with an outlier, but then it's really, in the linearly case, unlikely, I would say. However, as we know, it's not really in practice very often happening. Right, so this is also more a toy kind of data set. Right, so with this, any other question maybe, as we are now in the Q&A session? Yeah, please.
How can you plot the line that you have found based on your model or something? Because is it based on the support vector that you can define that line?
I see now all the questions come because we didn't have the theory of establishing that, right? The idea is now going through all the theory, and you can still play around now with the other one, which is non-linearly separable. And I will explain all of this. This is, of course, why we need the mathematical theory behind support vector machines. Because in a way, it will be a very systematic way that the line will be established exactly in the middle. So you could use the support vectors, and then just half of the margin would be your line, right, in this sense. But of course, there's more math behind it, more interesting aspects where we can develop a better idea of that. But let me come to this in a moment. It also reflects to the fact that we want to have more sophisticated models allowing error, and then the support vector switching between different aspects. So it's not always that simple, as I explain here, of course, but this is just the simplest way to start. However, what I wanted is to give you already some practicalities in the hand that you now can use the serial one while we basically have the theory, always again and again do some modeling, and basically don't just stop at this kind of data sets we discussed here. So the next step clearly is to use the non-separable data set, right? So class 2 and 3 here, that would be important. And basically then we have also the other ones that we discussed yesterday, right? So this would be the Rome data set, and basically then also the one from Indian Pines. They are already there, you remember, in this directory. And if you see here, they have also training and test sets, all libSVM format. So now you can basically, while I talk long about the theory, in the back, here and there, actually we will stop also, make some breaks here and there, but always use, the new data set. But start first with Iris. Now we have done the linearly separable one. Then we switch to the non-separable one, right? Just exchanging here basically the number. And then you can start with Rome. Now Rome is 9 classes, if you remember, not anymore 2, very not linearly separable, and you will see some very interesting surprises in the accuracy. We will stop then and we'll discuss some of the results, and I will do it here in front together. Just, of course, some of the questions were alluding to the theory, that's why we have to also go ahead with this. Right, so the location of the data sets, as we discussed yesterday afternoon, is also in the classification directory Rome, or in the classification Indian, right? And then you can use always the training and the test set. So some of that was raw data, some of that processed data. And when you think about now this file size and so on, what would you expect if you start the libSVM now? Anyone? An idea? Why we need parallel computing? It would be probably taking a long time for the normal libSVM, right? The serial one that has to digest now all of these data samples, this will take hell a lot of time. Still, you should try it to see basically now the limits, to really face the limits of this in order to experience, okay, that's something where we need parallelization, where we want to be, right? This is a tutorial not only for machine learning, also on the intersection for parallel computing. So shortly I will do with you the kickoff of the linearly separable example. So we again use SVM train, minus t, 0, minus s, 0. We need the training set. This time we use the one with 2 and 3, right? So this is the one we can start with. And check shortly that we have not something forgotten. Training file with the options, that should be okay in this particular example because it's a very trivial one. And here you see already an interesting aha effect. Total number of support sectors 27, right? So this is already alluding to some interesting stuff. So we have now a linear kind of model that tries to fit a non-linear case, right? So in a sense, what we will create here now is something like this on this, what we had already here on this slide. We have now the second part, and the support vector machine model now is of course not anymore very simple of picking, very little points of saying these are spanning the margin. And we will talk about this now in the theory. it's basically also saying, okay, lots of these internal points are contributing now to this linear line. However, it's still a hard margin, so no error allowed. This model is somehow dubious because we cannot have a linear model without any errors in that. So the support vector machine is basically at the limits here. That's why it's also time to go to the theory and extending then the support vector machines a little bit, going away from the maximum margin classifier to the support vector classifier, where you can allow errors to happen. However, there's a model file. If you look here, let's have a look on this. Also there are not, let's say, much surprises inside. You have the number of support vectors. We said it's a linear model, so basically very bad for nonlinear case now. Not allowing errors, so the total number of support vectors 27. So in terms of accuracy, what would you expect now?
Less accuracy.
I'm sorry?
Less accuracy.
Yes, but a little bit less? Right? A little bit less or more or less? What are people, what is your gut feeling?
5%?
Not too much. Not too much, probably.
Okay, right?
Not so much.
Okay. Yeah, let's have a look. You know how to do it. SVM predict. Not forgetting now the test set, right? That should be always first. We use the model that you created on this nonlinear separable case, and you maybe can do results and change now the name, because otherwise you will overwrite the results of saying maybe you want a non-linear case. It still is 93%, right? So it's just quite nice. So it's like has just a couple of points here which are misclassified, right? And still you see the machine learning is very good with actually the minimum of a support vector machine in a linear model. This is of course a toy data set. And a little bit you can see it automatically when you look in detail really what's happening. And there you can see the number of 4 in the classification that are missing, right? We had like 4 are missing. And when you look a bit careful, this is the real data plotted, right? You can kind of observe that there are 2 green ones very much in the other space and 2 red ones very much in the other space, right? Almost this, and this is of course different for all the data sets. But here you can see that exactly this was happening with the line. So the support vector machine creates a line with this and allows error to happen in this sense, right? So this is an example how the machine learning works. However, we have to now know a little bit more how really support vector machines are created in order to do that. Right, while I'm talking about now the mathematical explanation of that and so on, you can play now around with Rome if you want, right? So in Indian pines. Of course, here and there I would point you a little bit to the theory to understand it. But here now and then for some of them that, for instance, are very familiar with the SVM and mathematical details, please go ahead, use Rome with a libSVM with a serial case. You will see it takes actually much longer. And then, of course, if you're not satisfied yet with this, use basically with a linear model the Indian pines. The same way, you copy the data from the directory there in the classification to your working directory and just exchange always the model and testing files. Any question? Yeah, please.
The SNT parameters should always be the same.
The SNT parameter should
always
exactly always 0 and always 0 because we don't establish the theory yet. We are at the, let's say, minimum of the support vector machines. We get more sophisticated directly after lunch, where we then talk about SVC and support vector machines with kernels, very sophisticated, and then have also with Rome much better results as you will have now using the linear model. All what I want to do is saving time, because when you put in now Rome, for instance, it will take time, and we don't have time in the whole tutorial to do the theory and do all the runs, and we need a whole week basically instead of just 2 days, right? So please here and there now look, use the time. I will demonstrate to start, for instance, Rome in the beginning, but then I will continue with the theory, and you can just do the predict and so on that we just done now. Again, helpful is to have your data set locations clear, which is here in machine learning classification Rome and Indian Pines. So one example is maybe also just copy them here, because they're not so big, but in the Indian Pine case, it would probably make more sense that you just reference them. And you can always use tab as a tab completion. So we can use SVM train, for instance, here. Train the model again, as the question was, they're always used in the moment minus S0 and minus T0. Then, of course, we use some training file of Rome this time. So we go to apps, Gent, tutorials, machine learning, classification, Rome, and there is SDAP area. SDAP is this kind of feature engineering, if you remember from yesterday, this mathematical morphology aspect. So this means this one is really already prepared, right? That's why it's still good for, let's say, serial SVM, and it's a good, let's say, feature engineer to get high accuracy. We will come to the Indian Pines raw then, that this is not the case. So here you can pick, for instance, if you want SDAP area all underscore training, .el, and that's it. And this is going to happen. Hence, we have to wait. And instead of just looking now and taking tea and sipping coffee, because we have still some time to lunch, I will do now some of the theory. So everybody has done the Rome. Okay, who has not done the Rome? That's this way, okay. Maybe could you help here and there and explain what the reason is? Again, keep your hands up so that the people see who has problems, right? Otherwise we can't help you. And it will give you here some iterations of the algorithm. It makes an optimization we will talk about later. So don't worry about this. In the back we will talk about now more about the theory. So this is something where we start now with the idea of the margin. And we have done this already in our minds. So now I'll formalize that for you a little bit. Right, and I will go a bit quicker because we spent now a really long time on basically the kind of practicals, and the theory is something also you can look at home. But I will go through it so that you have a clear indicator why it's basically working. So what we said is the margin is now important. Hence, these points of the margin here are called support vectors. They creating this margin, right? And we will see that will be very much varying depending on what we allow. But this is the key idea and the result that you have done now already with the model in the linearly separable case. So let's go and question ourselves how we create this margin. And there's an interesting geometric, let's say, point there of saying how you basically create such a margin. And this will be now a little bit mathematically, but however it's very friendly in the sense that it's mostly related to dot products and projections, right? So the things we had yesterday introduced, if you remember, the dot product is a scalar. That is quite nice, so we can use that. And this is how we establish it. So when we take the space that we have here, for instance, in this example, you would have this linear decision boundary, and we have some positive examples and we have some negative examples. We could find the W that we always put basically here perpendicular to the plane, or orthogonal basically to this, and another one which is sitting here. So when you think about what is the projection property of the dot product between these two vectors, just to recap the theory from yesterday, this is basically then what you have in terms of length. Right? So what we now can say basically is, depending, W is not clear yet, we have to optimize and find it, right? But we can put it somewhere in the space as we like because we basically want to optimize it later. But if we say we have a new point, like unseen, right? It will be our future points. We try to get now into the space of out of sample. This would be new. Then I can use the projection capability of saying, well, you're left on the plane or right from the plane, right? If it's here, we use a projection and say it's left or right from the plane. So this is the kind of first in a couple of mathematical developments which we have to go through, right? That's hence questions. Let's do that at the end when we can reflect on all the different 4 steps, right? Because it's really mathematically in some points, but it is really coming obvious when we think about this. So we determine this basically with this first rule. We say this is a decision rule now, where it was a question how this line looks like. This would be W dot product B plus a kind of bias, and say, let's say positive when it's plus. So we can always say that because yet these are unknown, and we will optimize it in such a way that this decision rule is true. Which means when it's plus, then it should be positive example, and then they make the counterpart, it would be negative when it's around here. Right? So this is a kind of first development, just making, let's say, a simple assumption here. It should be from the projection over a certain kind of threshold, and now we kind of putting that around, right? And putting this inside the equation, so that we have basically 2 kinds of ways here how we can do that, using our label. So how we do this is basically we say first constraint, and this will be then a constraint optimization problem in math, which basically means that you have positive example when you do this on this part of the equation, and when you do basically the negative example, you establish this. That are just constraints that we can set on the optimization process which will take place, because W is not clear. That is what we then found out. X is a constant, right? That is something what we have in our data set, right? And so that's how we basically create these pi. And don't carry around always these 2 rules, which in a way is a little bit, let's say, complicated. You could just use our labels and say again, yi for the positive examples, like we did yesterday in the perceptron, are positive, and yi are minus for the negative examples. And when you put this in front and basically use this kind of decision rule, you come to the point that when you put in now just a -1 in front of it, this will be changing to such an amount that you have just one, let's say, part here. And for the support vector itself, that we will say, we can just establish then they should be equal 0, which means here the space, they would be positive, bigger than 0. But for the support vectors, those fellows which are really here on the plane, or on the margin corners here, these support vectors get set to 0. Right? So far you're following, right? We can set that because the optimization will still take place. So what we established now is for the algorithm some certain rules how he should take into account the kind of setup that we have here. Yet W needs to be defined. So we come to the next step of the development, where we think about how is now the width of the margin, because this is we are mostly interested in. Thinking about that we want to, what's the idea of the margin? Maximizing the margin. So we want to have a handle on the margin, right? So how we get the margin, we established this already on saying W is always perpendicular to the plane, or orthogonal, how you would like to say. So this is a helpful quantity if we put it here. And when we now use again the projection capability and using this kind of statement that we said the support vectors are on the corner or at the edges of the margin, we can just use one negative example and one positive example of a 2-class problem, right? We will extend to multi-class towards the end of the next lecture, and then basically you would have, you can make a statement of this kind of vectors that are here and there. That's an x to the positive example vector, and basically here have a negative example vector. You take the difference of the vector, so everybody sees, right, a little bit from this, that this would be then this line. So you take x plus minus x minus. So you come to this interesting fellow. And when you take the whole thing here and do the projection on W, you basically get here the kind of projection that you want. And what is this? The width of the margin. Right, so this is of course all now mathematically established. Now you can do some certain tricks which with a projection on it, right? And here it's very hard to see, but here you see the dot product, right? Sorry for that, it's a little bit hard to see. So you dot this with that. As we said yesterday, that gives a projection, a scalar value, the width of the margin. So for mathematical convenience, we can now put in basically the rules and optimize here the unit vector, because we still have to optimize it anyway. So we can say it should be something like this, because it will help us later in the development of basically doing maximums and minimums, right? Because how you define a maximum minimum of a function in terms of gradients, you would do derivatives, right? Or finding now kind of this. However, this needs to be still established. Now it's getting a little bit mathematical. I see already that people are concentrating. Very good. The idea is now we enforce these constraints, right? So you see that in x positive example, y would be positive. X dot y, that is this fellow here. We put that basically over 1. We have it on the right hand side. But here the b is kind of negative, and we put it on the other side. So that's how we come basically to these two fellows of the idea, right? That we can use a positive example. Of course, we have here to use -1 for the yi, to put that in this dot product here, in order to get basically then this kind of 1 plus b. And this is because mostly it is also including this minus, right? So this is, I hope, obvious that you just put it in, basically. We enforce our constraints, put that in the formula. And then for mathematical convenience, as I said, we put here 2 because we want to find the maximum. However, if you know a little bit about mathematics in this sense, it's now getting to some optimization courses perhaps, it's a bit like maximum is always hard. So much easier is a minimum to find, right? And so what we do here is basically saying that we want to maximize the margin and can transform that of saying, okay, we kind of just do the other way around, right? It's equivalent of saying 1 over w, of minimizing just w. It's the maximum. Again, for mathematical convenience, because we take the derivative, there would be then basically this to the power of 2, and we put a factor 1.5. We can always do that, because in the end, w is unclear and will be in the optimization process, right? So this is our constraint. We force on it to find it. Now the extreme values, what you do take derivatives, right? Still not so hard, but when you have constraints, you cannot just do our normal derivatives. And now what you do, you put the mathematical toolbox, so very smart people have already found a solution when you do derivatives of a constraint, right? A constraint optimization problem. That's really where we are, right? And much more mathematically I will not go, right? One level deeper will be then sequential minimal optimization, how that is solved and so on. Would be too much for that course, right? But this is something where you go in the mathematical toolbox of using Lagrange multipliers for these constraints. So that's something where, you know, I have to point now to a lecture on this if you want to know more, but you can see that for each of the constraints in 2 that we enforced here, we're using now Lagrange multipliers, right? And the interesting property that we will find, and this is done like this, you have here, this is the Lagrange, the multiplier that you do, we do our, let's say, optimization that we just have established, we want a minimum of that, and then you add up kind of the constraints that you have, and put for each of them the Lagrange multiplier. Now the interesting thing that we will explore is these Lagrange multipliers will be mostly 0, right? There will be only a couple of them surviving being the support vectors, and this is an interesting property why we can do very sophisticated things later. However, as you know already from normal derivatives, of course, we set extremum. In order to get the extremum, we will set things to 0. The problem is now, as you see, we don't only have w as the unknown, right? The others are constants, xe, yi, are our data set, right? The Lagrange multiplier is to be found, but still to put the extreme values, the minimum that we are interested in, we have now 2 unknowns, and that means partial derivatives, right? So this is now going really in the optimization mathematical space. You basically just do that. You take the derivatives of this interesting equation that we have here, the Lagrange equation. You differentiate it with respect to W first, and then with respect to B. Right? So you have kind of two derivatives, which is nice because they all have then certain properties we will look into. So we first differentiate and get in basically this interesting term here, because mostly we look where W is here, right? This is very much, that's why we put the mathematical convenience to the power of 2, because it will happily with this 0.5 equal out. So we have a W here, and here's a term, if you multiply that out a little bit, you will see W is just 1, linear will be removed from the derivative, so we end up with this term, and the other one is not really contributing to W, will be automatically away. So this is our first derivative that we set to 0, right, to give the kind of the extreme norm. Then basically we transform that a little bit, just put it on the other side, and this is now a particularly interesting thing, because the width of the margin is a linear combination of the samples. That's already an interesting takeaway. So we put it in the red box of saying this is very important for us later on. Hence, we have still some work to do. And the work continues here in the second differentiate, which is B, much more simpler. As you see, B is nearly nowhere present. This term will be completely vanished. If you now take the derivative and go to B, okay, we have this multiplied. We end up with this interesting term. B will be, of course, removed. We set it to 0 and have this interesting property here for this derivative. Still, we take into mind that this is an interesting property, because mostly we are also interested in knowing this, right, the width of the margin. So this is the fifth step, and now we go to the aspect where now we need a toolbox, basically inside the libSVM. That's what you have just done. Basically inside the libSVM. It's called sequential minimal optimization, quadratic programming, solving this. And I come to in a minute why is that it's the case. So here you take just now the advantage of knowing now what basically the width of the margin is. You put that in, basically inside the formula. We find the minimum. And this is in fact a quadratic optimization problem. So this is already solved from implementing. You don't need to do that. The libSVM has an implementation of it. And if you do this now carefully, you end up basically with these terms here in the original equation. And then basically the B you can use as well, because we had also for there, if you remember from the derivative, some interesting insight. Plugging in this helps also to a little bit make this smoother. Next one, when we look and kind of see B was 0, it equals out, right? And what left is basically this aspect. And oh, they are the same. And this is really now the quadratic aspect that comes into mind. The quadratic programming ending up, basically, if you take this now together, you have to be a bit careful with the indices here, right? So you really have 2 times everything. Right? You go twice through the data set, so to speak. So which means you have an I and J here in the indices. However, that is not necessarily the most interesting thing. This is by far then the most interesting aspect, which just takes us later to the kernel methods, why that is possible, and so on. We see that the optimization of all of this is a constant, right? The alphas are to be found. They largely depend, which is the biggest chunk here, just on a dot product between our samples, right? And of course, depending on how much samples you have, this could be now a very big thing, right? There's a computing happening, so to speak. And this equation is now solved by a quadratic programming package, like for instance in libSVM, there's an SMO, sequential minimal optimization inside, that we're solving you with having this Lagrangian solved. So this is basically how the SVM geometrically is kind of, creating this optimization problem. Let's see what we do for the decision rule now, because what we wanted to find out was what is now W, and we know W from our mathematical chains of working. So let's put that in, and we see now, interestingly enough, also the decision rule depends on the dot product, plus of course the point to be kind of coming. So in both cases, in the optimization we have the dot product leading the way, and in the decision rule we have the dot product. And this is an interesting property which then in lecture 5 will come and bring us a possibility of going to kernel methods, very sophisticated things. Here we stay linear, as you see, basically from the equations, but then we can plug there in interesting aspects like kernels and so forth. But this is really the fundamental basics, right? So looking on the time, we go a little bit now through some of the conclusions perhaps that you can see from this geometric interpretation. I go a bit quicker because in a way it's repeating some of the messages from the geometric interpretation and things we've done in the practicals already, right? Think away we know it's the simplest model. This will remain, but this of course is interesting now for our dot products, right? It will be big matrix in the end that we compute. And this a test vector and so on and labels, a bit is the kind of wording here a little bit different, which is X star for test sets, but this is not so much for us as a problem. Just for you some visual representations, what it really means, right? And you can see here, for instance, the different lines that we have created. There are 3 possible hyperplanes, and of course, this is, you know, the one where now the support vector machine is creating the one line that is actually very much interesting for the support vector machine, right? There would be perhaps someone algorithm would have done this, right, like the PLA or something like this, but the support vector line would have the intuition of go better to this line. You can, let's say, have all the different lines, of course, have then a kind of different mathematical kind of formula in a sense, of course, but that's not so important in this particular use case. We established in the kind of mathematical derivation that we have this margin now found, right? So this is now something very interesting for us. So we know the width and we know how to minimize it with the derivation that we had. And now we just have to go through the points and actually make that going to happen in the dot product. We have the points, they are basically in our data set, right? And so you see that the classification technique is then playing around with this. And this is a stepwise thing, what you would say, right? The optimization process is now similar, like perhaps a perceptron learning algorithm, thinking about what is the minimum, basically from the optimization step. Still, from us, if you remember, we're interested in the maximum. Right? Don't get now weird that the minimization process is in the math. Of course, for us, would be equivalent of maximizing the margin, but it probably has one solution here, then it has the better solutions coming to this because it has a larger margin. Right? So this is important, and these are then now the support vectors that change, of course, here and there, depending on where you are. Basically in the data set, and at the final end, when the optimization will find the best way, and will report that after lots of computations, and optimizations and derivations, then you basically have the one and will report the support vectors that kind of define your margin. Right? This is then set in stone, and then you can use a decision rule to classify. Here's an example where 3 of them are basically support vectors, right? The interesting thing is then all of these don't count anymore, right? They have no effect on the plane. So if you think about you sample some of them out, the algorithm would still find the same hyperplane. Right? It is just crucial when you remove this data sample or the support vectors, then of course a line would be different. Right? Because this is an interesting property. It's an in-sample property of support vectors. Right? If you remember k-means or so, k-means were just a mean. There was no, but k-median then had a kind of in-sample property with a median point. But here we have also an in-sample property which allows lots of interesting things which we will see also in the lectures after lunch. So in a way we have then basically this maximization that we turned into a minimization problem. Also this was something what I had already in the geometric thing, so I'll skip a little bit of this. We had the Lagrangian, of course here's your big data impact, right? So here is now where lots of samples, transpose lots of samples needs to have a dot product with. So this could be, of course, if you have a very large sample size, take a long time, and you have quadratic programming. But the point I want to make is a little bit here, you know, take into account that SVMs with big data could be a bit challenging. In the end, it will look like this. You have a big matrix to solve, and the interesting is that the quadratic coefficients, the alphas that you get then, of course, for QP, you put this in the QP package like libsvm, and it will come back to you with those alphas which are, it come back with you with all alphas. But all alphas, the majority of them will be 0, or almost like 0, 0.00 something, right? So from the optimization process, sometimes it's not exactly 0, but the key point is that they should be then set to 0. And in this sense, many will fall like flies here, right? Many of the data samples, because what you report back is then kind of a couple of them. But the in-sample property gives us interesting generalization measure. That's something we also talk a little bit about model complexity, right? When we have now 10 support vectors for 1,000 samples, that's okay. Then the model would be not so complex, right? You can imagine 10 support vectors optimizing this is, let's say, the model should be probably very well. Now, if you have a situation where 500 support vectors for 1,000 samples, roughly, right? That's a rule of thumb. It's not mathematically established. But if you have then 500 support vectors for 100, then it's very bad. And why? You have to adjust to all the support vectors basically the margin. And now you think you have 500 of them, right? The optimization process is going nuts, so to speak, while doing this. And by this, chances are that the margin will be by 500 support vectors, perhaps very small. And that's not what we want, right? In a sense here, you would say less support vectors better, because there's a more flexible chance. Of course, too little support vectors would be the other side, then it would be really not good. Okay, right. And of course this relates then to overfitting, right, this part here. And it gives you if you fit 500 support vectors, your margin would be very small. Then we are mostly at the perceptron again, right? Then we don't have anything from a maximum margin. So basically that's a key problem that we arrive there, and it gives bad out of sample performance here. Just for, now connecting things of the theory to the support vectors, what I said before, also here you see it's nothing else than in our hypothesis set, in our skill set is now the maximum margin classifier and quadratic programming contributing to this formula. So we exchange just PLA algorithm. Now we have interesting solving and limitations which now point to the aspects after the lunch, because now it's also time for breaking for lunch. Now think about that, what happens when people move here. Right, so this is something where, we have non-linearly separable data. That's what we will talk about after lunch. And, then there can be not really a separating hyperplane created. So what we do then, right, like this. One chance is removing those outliers, could be. But another chance is just waiting for after lunch when we talk about basically the support vector classifier, which then has a cost of actually allowing the violations. Shortly before we take food, I would say, now check again Rome, what's coming out, right? So everybody of you should hopefully now get something out of it. You see some optimization processes that we just discussed in theory. So the optimization process was creating this margin, going lower and lower. Oh, okay, there's a job killed wall time exceeded. Jesus, have you a wall time on?
You get 1 hour by default. Yeah.
1 hour, okay. Well, I didn't used to 1 hour. I just executed.
If you submit an interactive job, you get 1 hour.
The interactive job. Okay, good, smart trick. Maybe we should have that actually communicated to everyone.
It's in the mail, they don't.
Okay, so this is a trap I just run in because you said I did an SVM train and just 10 minutes ago. So I was wondering why have I now the wall time? But of course, what we did before was a Q sub interactive, if you remember. And I did this 1 hour before, and now I'm automatically, killed. Hence, it's hard to get on my job, I guess, right? That I got there.
Well, the results will be there.
Yeah. Okay. Well, let's have a look on that. So we can. Let's see. Do we give something out in the output? Where the location is?
If you didn't redirect the output, no. Then you only have it in the terminal.
All right.
You can just scroll back up.
Yeah. No, I mean, basically we have the model right here, right? So in the sense it's your own directory. And we don't want to use more because we see it's probably much more support vectors that we have now with Rome. Right, everybody has SDUB. Who has not the SDUB model created? Okay, otherwise just raise your hands, and during the lunch break now we can help and, you know, help there and just shortly discuss it before we break. You see here the different labels, a 9-class problem as we said yesterday afternoon, right? So no surprises here. Number of classes 9, we use a linear kernel still, and the total number of support vectors is already quite something, right? So we're not anymore in a toy example like the flowers or so. And this is now interesting, and you see here again the support vectors are of course really those in sample, and as there are 21,000 support vectors, of course that is a huge file. You see that best when you do more and then using this file. See, it gets on and gets on. These are all the 21,000 if you want, and control and check it. However, we are more interested in the SVM predict. That's why, because before we go now in the break, perhaps it's good to do this. But in the break, feel free to. Oh, wait a second. I first have to do another Q sub, right?
Yeah.
Sorry. Yeah. So that's something you should also not forget. So before the break or in the break, now play around with this, right? You have the Rome data set predicting, you have other data sets, and in between we take some food probably, and then we continue afterwards with a discussion of the results in lecture 5 and see how we can improve the maximum margin actually by doing this. The SVM predict was very simple, just use the model file, the testing file of Rome, and results somewhere written in, and then it works. Okay, any questions perhaps before we break to lunch? Okay, going once, twice. Okay, no questions at all. Then basically we break for half an hour, right, for lunch, and then see you back. Maybe for the simplicity we say 1:45, right, before having now.
1:45.
Yeah, 1:45, exactly. Because we have now a kind of time. So 1:45 we will continue, also for the online audience, with lecture 5. Feel free to try that out all the time. Remember this, that your interactive session will cancel after an hour, right? So if you now start Indian Pines and the raw one, it could be that you actually, depending on which SVM parameter you choose, over the day now that we will learn, you will basically go over an hour, right? Especially when you think about testing and so on. So it could be the case when you have done things before. Always think about that you go and run against the wall. How far are we with the recording? Is it all online? All right. Okay. Cool. Right. Then let us proceed. So I just asked the audience basically if there's some feedback from Rome, and I think we realized that in terms of Iris it came back directly to us. The answer now in Rome it took some more time. And how many minutes it was taking for Indian Pines? Do you have an estimate on that? Sorry, the Indian Pines, roughly?
No, I let it run during lunch.
Yeah, so during lunch, like half an hour, maybe 20 minutes or so. Of course, we want to improve that with a speed up, right? Now that's the idea. The other part of this machine learning tutorial is now not get stuck in serial algorithms, right? So we will switch now to the parallel algorithms, PSVM. And before I proceed with the lecture 5 of going to more sophisticated models with support vector classifiers and so on, we would start now the parallel part. The reason is because it will take time here and there. The runs will take 15 minutes, half an hour, and we want to do something in between I talk. So let's start with some of the parallel runs now before we continue basically with the lecture 5. So for this, as you can imagine, we basically have 2 scripts now, right? And I make them available for you just after really discussing this. And if you have, for instance, you can put your Rome, Indian Pines. Don't use Iris, right? That doesn't make sense anymore in parallel. But here, for instance, I put you the example of Indian Pines, and I will make them available, the job scripts in the scripts directory. Just going quickly through. Right? What we just had yesterday was we had HPDB scan, the module, this, what we now have, is PSVM, a different module you have to load for that. Of course, that's pretty obvious. We still have my MPI here. And the same principle, in a sense, is that we need some data. But now, you remember, we have 2 times data. We have training data and test data. Hence, for the job script in training, we need the training data. Right, which is this interesting fellow here, that you copy then in your directory. For instance, in Indian Pines, you have this one, but you can also use Rome SDAP processing that you use in the serial one. Right, so this is something what you can decide on your own, and actually maybe you can even do both, submit them. You can then play around again, as we said yesterday, with these nodes. Hence, you for these big ones here with the PSVM, you don't use your interactive session, right? You do again the QSUB with the job script. The interactive session you should just use for libSVM serial. However, the PSVM internally has also support vector machine, which is implemented with libSVM. So you see basically the parameters that you have here, T2 or S0 stay basically the same. And we will now explore over the day what actually C stands for, what G stands for. So M and O and Q are things which are related to the parallelization. We don't touch that here. It has something related to caches and how we parallelize that. So it's not really the machine learning part of it. So ignore that for a while. And also minus D stands for sparse representation, what you should use. So these values you should just basically take up and use as well. And with these we can play around. These are the support vector parameters, right? And when you do this, you have the PSVM train. The hybrid is just an example. You don't need to do this. Here specifying 32 ranks explicitly. You can also remove the hybrid and just play around with this, right? 2 nodes, 1 node, or 1 node, 12 processes per node. And you know, this is kind of the training phase now. What comes out of this is now a bit tricky because we go remotely, right? We now submit QSUB, and you remember yesterday we had this interesting sandbox created here in Scratch, right? So that means the job has its own playing field. In other words, when you then do the training there, and you remember what comes out of the training, who remembers what comes out of the training? Get you up from lunch active? The model file, exactly, right? The model file will be there. However, in the serial case, it was in your normal directory that you have, your home directory, wherever you started basically the job. Here, you have to go back in the work directory, right? So it's a bit inconvenient for us. And why is it inconvenient? Anybody has an idea? Now we have a next job. Yeah, please.
Because the job ID is different every time?
In a sense, yes, exactly, alluding to it. So the job ID is different every time. Now, if you think about, we have another job for testing, and we need the results from another job from training. So take aware of this now, right? We create a sandbox. We put in this sandbox there on the left-hand side in training the model file. And now we come to a new process, which is testing. Completely separate, has nothing to do with the job before, except we need out of the sandbox this model file created, right? But the job is completely independent. Hence, we have to now do interesting things with this, like you see here, that you have your model data always to be linked from this interesting sandbox. This is possible, not a problem. And at the end, you will see from the training always this statement. It says results available in this work directory. However, this work directory is a job ID directory, which looks a little bit like this, right? I'm this particular user, and you basically have there a kind of temporary job directory, and there would be then the model somewhere inside. You can also put it in your home directory. That would be another possibility, so that you, once you finish the training, right? The work directory, it will show you where it is, you copy it to your home directory. But this would be not necessarily always the best thing to do, how many jobs you have. So one idea could be that you specify then this work directory that you have from the other work here, and just use the model there. Right? This is one thing where, you know, that is a little bit more complicated now, let's say, compared to the HPDB scan. Yeah, there's a question.
Maybe it's simpler to just combine both tasks at once, yeah?
In a way, yes, but basically the problem is that the amount of cores could be useful to change in the testing. We will see that the training is relatively okay still, but we had the rule also over lunch discussed. We have something like 10% used for training, 90% for testing. You will see in the data set the testing data is much more bigger and needs much more time. Hence, that could be useful to increase the core much more than in the testing, and the training doesn't make sense anymore. The aspect you're alluding to is in a way a good idea, with chaining jobs. And there's a possibility in some of the schedulers to do that. Here we keep it for simplicity separated because it's also 2 steps. But when you go to production, you can do some of these tricks and these tunings. Right, so, but let's go quickly through the test. Oh, there's another question. Yes, please.
I was wondering, so the testing, it's basically just applying the model that you already fitted. Does it take a lot longer than the training, even if it's just applying the model? Not optimizing it?
Indeed, yes. Yeah. And the reason is mostly because it's much, much more bigger. Right? The reason is mostly 10% to 90% the cut. If you now would have a data set where that is not so dramatic, this kind of cut, then of course the time for predicting, as you rightly said, is just by applying the model basically very trivial. Right? And in fact, there are like other parallelization strategies that you could think of that you can parallelize that beautifully and scales beautifully because it's independent. You check now basically for each pixel from the samples independently from other pixels if that was correct or not. Right? In a sense, this is a very good question because the processes are different. Right? This one is much more HTC. Still we're using a HPC machine actually to get the benefits, but the communication between them is very rare. However, it takes still a lot of time because the data set is just much more larger. That's the key message. Hence, it makes sense to do more and more cores there. You can beautifully parallelize that, and therefore get extremely more speed up than in training. Right? That's interesting. Good, but another question maybe before we go to the testing script. Right, and also when you do this now practically, just raise your hands, right? We do it in front together, but if there's a problem, just make yourself visible so that we can also help you. Right, so let's go to the testing. The testing is almost the same as training from a job script perspective, roughly, right? We have the same things. Wall time, nodes needs to be specified. We don't care about HPDB scan. We care about classification today with PSVM, my MPI run. We work in our sandbox. This sandbox is another sandbox from the training, right? The training still is happily sitting on the one side with a model. Now I'm creating a new sandbox, testing, for my testing job. And then I get here the data. It doesn't matter if you took it directly, basically, out of the other job, or you copy it maybe first, like I did here in the home directory to show it, basically also later. That is basically the model file. The testing data is important here for getting, your samples which we throw in the corner. Now we take it back to evaluate the model of the accuracy, everything you know from the serial case. But here we have to specify that in the job script in order to get it remotely computed. Right, and then here also you can play around with the hybrid, but not necessarily. You can also remove that. And then PSVM predict having basically the test file now available because you copied it in the sandbox. And having your model file is available because you copied it in your sandbox. And then you put something as a result, if you want, where you have the kind of the samples going in. And when you run this, the output of the job should give you an accuracy. So this is something which is not now interactively going to your screen, right? So we have a serial lib SVM. The finishing of SVM predict was always accuracy something. So when this job finishing, you don't see anything, right? It's somewhere remotely. Hence, the output is redirected to a file, right? And I show you a little bit when we walk together through this. Just take away these kind of points. Right. So before we go into the video and everything, let's go the parallel way so that we have some submissions we can work on later, because some of them will take time. Of course, it depends on how many cores you use here and there and how many nodes. Especially some of the processed one could be very quickly done because they've been pre-processed. So the first thing I'm going to do, I copy these scripts that I just shown to you, which is the PSVM train sample example and the PSVM test example. These scripts in our typical apps, scan tools, machine learning, web classification, scripts folder. So now basically you have in this directory both of these scripts, and always use them in different jobs, right? That is important. And you have to tune them to your needs, basically your own directory where the model file is for testing and so forth. Don't forget that. But if you look here now in scripts, that is basically what you have in the scripts. And now you do the opposite what I did, just copy these scripts. You can do copy star if you want, because there are no other scripts in the moment, and put them to your home directory. Right, like copy star to point, for instance. When you are in your own home directory, copy star to point. No, sorry, no, you have to copy, of course, and this one, contents from there, star, and to point. Right, this copies, if you are in your home directory, not CD, sorry, the font size is just very big. So you copy basically all the scripts to your home directory, that's the task. Yeah, let us know. Is there a problem of copying the job scripts? Everybody has done that or know how to do it? Who has not done it or has a problem? Okay, no problem yet. Excellent. Good. So I see some people are still working, so let's wait half a minute or so that all people can follow up. Okay, so let's go a little bit ahead. So now that you have all the job scripts, basically remember to swap, right? If you not have done so, module load, module swap, cluster golab, before we submit anything. Now you basically have no dependency with your interactive job anymore, remember that. So what we start with would be looking at the training. So let's open the PSVM train example. It would be perhaps this one. And we keep it maybe to one node here in this example. And what we want to see in terms of training data is, for instance, here the Indian process training, which is already the processed one. So this would be quicker, right? So it's okay, you're using, for instance, just one node for it. We probably want to remove this hybrid here, then the automatically most amount of them will be used.
Remove the 32.
Oh, yeah, I did. Hopefully, I thought so at least. So, yeah, thanks for the feedback. So and here is the same thing we discussed on the slide. PSVM train, -D, and these kind of options are for, let's say, more internal things. Now, interesting things are these here, right? These is something which we don't know yet, except these two, right? And now my lecture 5 will introduce you to this -G8 and C10. What is these fellows? So in the moment, just basically put their zeros in and remove the -G. and basically also do a 0 here, right? With this we have another linear model we create out of the data with the same support vector machine type using Indian processed training. Also ignore the -m, because the -m is essentially just the caching mechanisms for us internally. Right, so again repeating, put the cost to 0, -t, 0, -s, 0. That's the same thing in a sense we did just with the libsvm in serial. And then use the Indian processed training. Okay, everybody has changed these parameter values. Is there someone who has not changed the parameter values yet? Okay, there's a problem on the back. Okay, anyone else who has not changed the parameters to T0, S0, C0? Okay, if not, that's the case. Then it's time to actually abort and actually to proceed. So here my interactive job was again actually finished. And
What are the values they need to use for the
0, -t0, -s0, and -c0, and remove -g. Right, so my interactive session was again terminated, so I have to do my module swap again, cluster golet. But that's really the only thing I have to do, because the other module loads are of course now part of the job script, like the module load PSVM and so on, right? So for those of you who are in the interactive session still, maybe it's perhaps better to go out again, right? Exit this. Now we want to go now more to parallel, more to sophisticated things. Exit this, you just type exit and your job will be terminated. Then you have to do again module swap golet. And then you do basically the things we just discussed with the QSub PS1 train example. The things we did yesterday also basically with our HPDB scan, it's the same procedure of using QSub. Of course, I just remember we probably want to use also the reservation, right, which we didn't have in the job script, so we have to add this basically to the QSub command. So instead of just using this, we have this kind of reservation, but we don't want an interactive session, right? So it's QSub. We have the reservation. Is that correct, Kenneth?
Yeah.
Moment? Yeah. But of course we need also our job script, right? Which is now the PSVM train example, SH. So not interactive session, batch submission as usual, now to the remote cluster with our training example. Fire, if you have done so with a reservation. Of course, remember a little bit your kind of job ID here. But it will be obvious also from the timestamp in your directory later on. And if you want, you can do some QStat of looking what's happening to your job. And usually this now will take some time until the model will develop, right? And there's no point in doing already predicting because still the model is actually developing. However, we have seen we are not really sophisticating yet. Hence, we basically want to come to lecture 5. There's one video which I would recommend to you because it kind of nicely summarizes lots of the topics we discussed. I don't want to show it now because we want to take more time for the practicals. And you can basically look at it at home if you want. It has an interesting aspect with showing a little bit more about the margin, an application example, text, and so on, and a little bit of the kind of modelings that you can do. But in a way, it carries the message that we had also before with the buffer zone and so forth. Right. So before we conclude now with this part, any question for the parallel submission right now? Before I talk a long way now about extensions of support vectors. Okay? Going once? Twice? People seem to be busy. Good. Right, okay. Good. If that's not the case, let's go to lecture 5.